I'm just gonna like leave the slides and not, but yeah, Mater was a big fixture in our home for a while. By the way, Alexander, is it okay to record this one if it's not being recorded?
Yes, yeah, I just turned the recording on.
Okay. So what's going on here? So I am not an expert in this. Again, this is just the day I'm going to tell you things I don't know anything about, but I'm going to do my best at it, okay? So if you really want to learn, I would recommend these authors in these areas. And the last person I recommend, because this is a CSU local, so you can walk over and talk to her. Well, maybe not during Corona, but she'll answer your questions, and she's a smart physicist. And she's actually building the materials that I'm going to speak about today in her lab. So you can walk over, if you're lucky enough, you get a tour of her lab and see her, she calls it her easy bake oven. It's like, you know, a $500,000 easy bake oven. So it's worth seeing. I don't know what background you might have, but phases of matter. I think most of us know that you should not give your loved one a graphite ring as a wedding promise. You're supposed to do diamond, and there's a difference, and they will know. So how do they know? Well, they're not going to know this way, but they know there's a material difference. The structures are different, the behavior is different. But at the level of like, what is physically the difference? The most successful theory seems to be the Landau taxonomy. So this is an idea where you say, let's look at the symmetries of the underlying molecular structure. And now you have to think of this a little bit idealized. So I've got a little picture of graphite. And of course, every piece of graphite is ultimately bounded. And so it'll have some sharp edges where you can't do anything because of the rigid structure on the boundary. But if you continue that out to like an infinite lattice in all directions, then this hexagonal tiling will be a symmetry that you pick up as a symmetry group element. And the same thing with diamond. If you tessellate that out in 3 space, you'll get a space group. These are differences that are material differences. They really do qualitatively say how the behaviors will be, the physics of these will be. You can see, for example, in the graphite that the pieces will shear apart the different layers. And this is why when you draw with your pencil, you leave behind some carbon, but when you draw with your diamond ring, it doesn't seem to leave any carbon, okay? But what about this thing here? So the idea is that groups, the symmetry groups, should characterize different phases of matter. And along comes this discovery of something called Herbert Smithite. And in investigating this, it has certain properties as a material. And whatever that material does, its behavior is sort of a little bit confounding. The more investigation people did, the more they discovered that some of the behavior really ought not to be described as a solid. Now, this is clearly a solid. It's a rock, okay? But what I mean by not being solid is, let's imagine what it would be to talk about a liquid in any kind of usual sense, like liquid water. If you're looking at the symmetry group of water, it feels like, how do you make sense of that? But you should think if there's a finite number, you know, Avogadro's number tells you how to multiply out and get the total number of molecules inside your glass of water. That's finite. If you extend it into infinite, you will see that same configuration somewhere else. And even if you just move a couple molecules left or right, you'll see that configuration somewhere else in this infinite extension. So you have a continuous translation group. You can move that shape somewhere else. So whenever you have a chaotic system that you can move random pieces around, that's a liquid. And this has that feature, that its symmetry group has a continuous parameter. And so in some sense, this should be a liquid. Of course, it isn't. So the key ideas here, they started being discovered in things like condensed matter physics and certain things like conductors, like what do you call them? Really cold stuff, I forget. The name will come to me, but like when you get really superconductive materials at very cold temperatures, things happen that are irregular, and they're trying to figure out why. And it came down to the idea that maybe the symmetries at the level of molecules is not going down enough. Although the atoms are a good stopping point, there are subatomic structures. And if you look at subatomic structures, you might discover that you have a different symmetry group, and that might be what's really going on. Now, why would you care about classifying phases of matter based on their subatomic nature, their quantum nature? And the reason is primarily because there's a lot of potential applications. Some of the main applications are to things like superconductivity, making really strong magnets. Quantum computers is one that a lot of people are excited by. It's not clear how close we are to that goal with these materials. For example, the easy bake oven I already mentioned, they're building tiny little molecules. They're not building giant machines yet. So we'll see. We have to work up to this. But I think the most exciting thing for most people is, like I joke here with a warp drive. it's what we don't know we could make with these new materials that will be the most exciting for the future. You know, we didn't anticipate semiconductors when we first started exploring chemistry at that level. Whatever these quantum phases of matter might do might surprise us with their ability to create new things. The summary of so far is that when you want to describe phases, one of the most successful ways is to break it apart based on the symmetries, the group together with its representation. You can't just have just the same symmetry group, but how it actually acts. People talk about symmetry breaking when they apply enough energy to reconfigure the molecules, and now has a different symmetry group. So they broke the symmetry. That's when you change phase. You melt water, you burn a diamond, whatever it is you're doing that changes the type of molecular bonding. It once was at the atomic level. We're now going subatomic. Now, you'll also hear the word topological quantum phases of matter. This has many reasons why the word topological gets thrown in here. For one, we do actually study this with topology. Studying chains of quantum interactions on a line, that's completely described by group cohomology. And not just H1 and H2, we're talking about Hn for an arbitrary n. So most of us in group theory don't even learn that type of homology, but apparently that's exactly what you need to distinguish quantum phases. And if you go to higher, like two-dimensional phases of quantum spin liquids, these are classified by Wen as they're what are called fusion categories, or symmetric monoidal categories with a few other axioms. And you may not even know what those words are, but another translation is that that's equivalent to linear logics. So now you're opening the door for a number of different people to study this from categorical means, from computer science means. It's the Wild West out here. We don't know what's going on. There's no general theory. Everybody's finding small ideas and putting them on certain applications. Topological quantum field theory is the substructure that defines this. That's another reason that topology shows up as a word here. So keep an eye out for almost any math subject at all could probably be useful in this field. It's an emergent subject area. So what do you need to know to get into this? This is a crash course in quantum mechanics through the lens of a mathematician. If you really want to learn the physics, I recommend Isaac Asimov. Why? I mean, a science fiction writer has creative ways of explaining things. So and you can read a physics book and it'll put you to sleep. But Isaac Asimov has various books on physics at this level that you'll enjoy. So that's why I'm recommending him over the real serious people. Okay, so this is a busy slide. I'm not even wanting to spend much time in here, but I think I need to introduce a little bit of notation. So what is a particle to a mathematician pretending they're doing physics? You would just say it's a unit vector in a Hilbert space. And the Hilbert space, the only thing I need to do there is I need to have some notion of length. So I need an inner product to come up with a length. We'll say everything's complex because it makes life easier. And so if I have unit vectors, a projective plane of complex numbers, I might just think of basis vectors, like these two crazy notations. This is called the Ket notation. This is the first basis vector. That's the second basis vector, which, as you see below, you could just think of as 1, 0 and 0, 1. There's really no reason you couldn't just think of coordinate matrices. It's just not done. You're supposed to write it like this so that you're with the cool kids. Now, once you have that, there's another one you've been taught. You've been taught that all particles have this duality with waves. And that can sound very mysterious. And perhaps it actually is mysterious. But mathematically, it's incredibly boring. Because all it's saying is to take your vector, transpose it, and multiply. You'll get a square matrix. And this image of the square matrix will be the vector you started with. And then the kernel will be perpendicular to it. So this is what's called the density matrix. And this is also the wave, the probability wave. So when you think of it this way, what's this particle wave duality? It's just saying that, well, you can use a matrix to write the vector. The vector in this basis. So it's not that mysterious on a mathematical level. I'll leave it to the physicist and Isaac Asimov to tell you what it looks like when you're living real life with this. Okay, now we got to entangle stuff. That's the cool part, right? Is when you get particles close enough together that they do something fun. What does that mean to the mathematician? Well, there are two ways you could glue two vector spaces together. You could sum them together, or you could tensor them together. And if you just do a counting of the states in experiments that happened, you could see that it wasn't summed. Dimensions didn't add. The complexity of the system grew exponentially. Therefore, it must be a tensor product. And that's now the Copenhagen Convention, that we assume that the way to glue spaces together is by a tensor product. So let's just look at an electron, right? You take hydrogen atom. It's got single electron sitting out there in its first shell, and it loves to have a second electron with it, we're told, right? And so along comes oxygen, which has some extra electrons to share in its outer shell, and it likes to share one with one hydrogen and another one with another hydrogen. What's actually happening? Why is hydrogen trying to share an electron, like 2 electrons? Why isn't it just happy with the 1 electron? It has a balanced charge and everything. The main reason is this. Take a look at what happens when I write down the physical equations as mathematics. To have an orbital of electrons, I need to have one that spins up and one that spins down. That's probably something you were taught, and even if you didn't know why, you just did it. So let's put that together into an equation and turn it into a matrix. If you multiply these out using just that row transpose idea, forget about the normalization. We just said things would be length 1. That's all this is doing. We'll see we get this matrix here, and that matrix has rank 2. Now, if you would reach into a bag of matrices and pull one out, chances are it would be full rank. If you pull out a 2 by 2 matrix, having it be rank 1 is incredibly unlikely. So rank 2 is what should happen generically. So it's not like hydrogen has a favorite wanting pairs of electrons. It's that if electrons are running around, they're most likely going to be rank 2. They're most likely going to be a matrix of the most generic kind, meaning entangled with another one. That's why what's really going on here is more about statistics and less to do with like wanting affinity of the language that was used in the early 1900s. You bond these together, you get the water molecule, and that has higher rank, therefore it's called entangled. Now let's get into the slightly lower level stuff, because this is going to matter in a later slide. How does stuff change? How do you go from something that was just a rank 1 matrix and make it a rank 2? How do you get 2 particles to entangle? The theory prevailing goes, this is something called the standard model, is that there's this thing called the Heisenberg uncertainty principle, that below a certain length, you can't do measurements precisely. So if 2 electrons come close enough together that they're below the Planck scale, that's a particular constant number, then you really can't rule out anything happening. They could borrow from time because you can't measure time to any precision. They could borrow from space and energy. So what can happen is that within that small scale, you can have what's called a virtual particle. It's a particle that pops into existence and disappears before you run out of the Planck scale time. And you can't prove it doesn't happen because you can't measure below the Planck scale. So these virtual particles, whether they exist or not, they have the property of doing something fundamental. If these 2 particles come close enough together and they exchange a virtual particle, then you took some random information from one particle and you passed it to the other one. The result is you have a deficit on the E1 and the E2. They've swapped some private information that you weren't privy to. The result is as they leave each other, they now know about each other. You think of them as being entangled. You think of them as having spooky relationships to each other. And in fact, all it is that they swapped some information early on in time. Somewhere in their history, they swapped some information. So if you were to measure one later in time, you would pick up the information from the previous passenger, no matter how far apart it was in time, no matter how much distance is there. So there's no information being transferred. There's no like, I turned this particle this way and then the other one immediately knew how to turn into the other one. It had already shared a secret between them, and you're just reading the secret between them. So a lot less spooky action at a distance and just a little bit more something happened that you didn't witness and now you're reading it. So that's how stuff changes. Now, if you think about this, this is always reversible. Anything that you could swap and not notice, you could unswap. And so this is what we call a unitary transformation. We want to preserve the lengths and we want it to be reversible. That's a unitary transformation. So on a purely synthetic level, we could model this by putting a little matrix here, a little 2 tensor or a 4 tensor, depending on how you model it. Particle 1 coming in and out, particle 2 coming in and out, they meet this 4 tensor, they entangle in some way. That's all that's happening. And we'll just write it as U times phi. What about measuring information? How do we know what's actually happened? It feels like somewhere these things are happening, and yet if we don't witness them, how can we know they actually happened? Well, the idea comes down to something pretty natural again. What we do when we measure is we simply put particles that we're in control of close by the ones we want to learn about. Okay, so if I put my little measurement thing on this little piece of metal in my circuit board, how does it measure what's happening to the electron? Well, the electron comes close enough by that it can entangle with the tip of my measurement. And this measurement here is applied to a material which is predisposed to like spin in one direction. It's ferromagnetic, for example. So if something swaps, it makes a little current. That current then makes a current in the nearby neighbors. The nearby neighbors have a stronger current. It amplifies. It amplifies up the system, and it prefers, therefore, that we see that as a result on the scale. So it's not like we just made the electron choose to be up or down. We simply saw that that secret exchange that happened whenever they were entangled has been amplified up through our measurement, and we now made that observation. We now think of it as having collapsed into that state. The truth is, it's in a mixed state the whole time. It's just that that's the one that got amplified. That's the state it's in. Any questions here? So the basic idea is, you can take all the physics you have and throw it out the window and just think about unitaries between complex vector spaces. If you pause long enough, that's a good enough model of physics, particle physics. So now let's talk about quantum phases of matter. How do we make materials that we can explore on the level of wanting the quantum properties to be exhibited at a larger scale, at a scale that we can use to make materials that do crazy things? So this quantum information is being exchanged so randomly between things, it should, in a sense, decohere. So much random noise should mean at the very top scale, nothing is preferred over anything else, and so we don't see the quantum effects. But some materials are bucking that curve. How do we get there? Let's go back to Herbert Smithite, okay? So Herbert Smithite has this really cool lattice, the Hagamo lattice. I forget how it's pronounced, but it's a lattice name I didn't know anything about. I would not be surprised that this has other names to mathematicians. I feel like John Conway probably has some clever name for this. but whatever the name of this lattice, you see these little Star of Davids everywhere. What's actually inside then? So each one of those little triangles has a bunch of little electrons that are spinning up or down. Now I've drawn it the way that the material actually is. It's called frustrated. They're not all pointing in the same direction within this triangle. It would actually take quite a feat to get all of these to agree at the beginning of making this material to all point in one direction and become strongly magnetic. And in fact, this material doesn't do that. You can measure those properties. And what is behaving like a liquid? Remember, we had this continuous symmetry group that was causing us to think of it as a liquid. It's this frustration. These two try to make that one vote down. But upon voting down, it triggers that someplace else is now frustrating that triangle. So then those other ones flip up. And they just kind of do this, sonnet all the way through, everybody echoing off of each other until they eventually just become a chaotic system. And you get this continuous parameter. But it stays completely coherent in that configuration. It stays in that phase of matter. The symmetry group doesn't change. So it's a stable substance with this liquid type property. Peps, this is perhaps my favorite. Projected entanglement, pair symmetry, or particle symmetry, depending on which reference you read it from. This one's really clever because this one is saying, let's bring these particles together in a way that's already maximally entangled. So you see I have a little, what's called a singlet, but think of it as an orbital, right? I have a spin up and spin down. That's a rank 2 matrix, so it's generic and therefore it's stable. It's not going to suddenly become one direction, right? That would be unlikely in terms of the measurements. So it's going to stay as a pair like that, and it's going to be happy being in that configuration. But if it's close enough to another one that's happy being in that configuration, then you reach that same little Planck scale where they can exchange some virtual particles. It effectively blows up the dimension of your complex space big enough to have an interaction. But then as the Planck scale collapses, it projects it down. So you blow up to a larger vector space, do your physics, and collapse. You never see the observation, but the result is that you've now communicated information from the top one to the bottom one to the left and to the right. Thus, you introduce a stability. Now, there was a thing that happened in the previous one. I should have said so. You see this little gap here? That's called a gap. When you have sort of entanglements in sort of parts of it, but not all places. And the topology of gaps, we think, has a lot to do with the large scale physics. We don't really know, but we're keeping track of it because maybe that matters. This one has no gaps. All these entanglements are happening close by. There are no gaps between this system. And this one is highly protected. It's symmetry protected because if I was to ever flip something here, all the neighbors would vote it down. So it's like a built-in error correcting code, right? Error correcting codes are sort of say, take the majority vote. It's a very simplistic view. But if all your neighbors want you to point in one direction, you're forced to point in that direction. Even if a little bit of noise, a little bit of energy gets added there and flipped you, that's a very temporary thing, which is great if you're trying to keep things from decohering. This is what's known as a quantum insulator. It's very difficult to get quantum noise, quantum random effects to go through this type of material. So if you're building a quantum computer, you want to isolate your computations from the noise of the world around you. You might line it with a quantum insulator like a Peps model. And actually Peps is a code name for a whole lot of states like this, a lattice structure with this kind of virtual interaction. This is the one that everyone wants. This will get you a Nobel Prize. If you can make this, you will get a Nobel Prize. So it's a theoretical idea that there is a material out there known as a Kataya anion. And the idea here is that you want to actually think about something that's quantum protected, so it can avoid noise from the system, error correcting itself, but allows you to actually move entanglements across the system. That is, you want to be able to entangle things far away. Why? Because what a quantum computer has to do is take a bunch of small changes and equip them to sort of move the probabilities further and further into a larger, more complex system. And then you measure the whole complex system and it collapses to a favorable outcome. But that requires that you do a lot of entanglements over a longer and longer and longer period of time or over a larger area. So wouldn't it be great if we had a material that allowed us to entangle at arbitrary distances reliably, wouldn't decohere, wouldn't take in noise from the environment? So if you can build this, this is called the Kataya Honeycomb model, this is why you'll win a prize. You're going to basically have built yourself the material, the copper or the silicone that you need to build the next kind of computer. Whether these exist is the whole question. We don't know. A lot of people think maybe.
A question?
Yeah.
So the topology of this thing determines the stable state or the higher scale state? Or what?
Well, it's a mixture of things. It's the topology and it's the symmetries that are emitted by the topology that affect the large scale physics of this. Within the physics, you might have what's inside there. Like, what I drew here in purple is an entanglement of two next door plaquettes. If you move that around the space, you can come back to yourself and you make a non-trivial, non-collapsing loop, right? So now you have a non-trivial homotopy. And that matters because then that you can measure as a physical change. And so you can start to store information in a quantum entanglement in this kind of a way. So the idea of these Kataya honeycombs is that they're sort of like a graph paper, that if you know how to move your entanglements around each other, you can start to make entanglements that you could really program software with, if it exists. But then the nice thing is it would be self-protected. Like it wouldn't just easily succumb to noise because all the surrounding things are voting to keep it stable. So it's only the energy you add that lets you write on this. Okay. So you can see why people would want it, but it might also be a little bit like a mirage, that maybe materials like this can't actually exist. We don't know. But the hunt is on. So what does the large scale physics do? Like, this is Amit's question. How do we get to the large scale physics from this? And this is the point of where I get interested. The answer is going to be my favorite problems. So I'm going to go back to the Peps model. It's the one that I know sort of the most about in this situation. I've drawn this as a 2D lattice, so it looks like you could put your finger right in the middle, but I'm just not able to draw a 3D lattice, okay? But you should think of the material as having a boundary somewhere, right? Just like any material is going to come to an end somewhere. At the boundary, that's where you can test the material properties. Is it magnetic? Is it soft? Is it whatever? Any property you want to measure about it is going to be on the boundary, okay? If you crack it open, you just create new boundaries. So it's not like you're ever going to see inside. So we'd like to know, what is the physics on the boundary? That's essentially the physics we get to see of the materials. And if we can use that, we might reconstruct whether that inside has the entanglements we want and so forth. So how do you get the physics of the boundary? Well, if you zoom into one particular particle, a neighbor to the boundary, the noise comes in from, or the interactions comes in from the boundary as maybe one of these little X's. Remember, everything's a unitary. So I'm going to try to entangle with this state with this property X, okay? And I've got to somehow get inside the interior of this boundary. So there's a way I could do this. For example, I could spit out a Y and a Z, just two different operators that are unitary on the other side of the wire. Or maybe I only use one of the wires that spits out on one side. But there's another option. Maybe it actually sort of smooths out like a heat equation would, right? Like, you drop something and then it kind of goes out on all the wires in different proportions and with different qualities, right? So these first few are sort of you know, the combinatorics dream, right? That everything is sort of like chip firing games, and like there's predictability of like comes out this way and that way, and you don't sort of smoothly move around like a differential equation. So are we in algebra or are we in differential equation land? That's like the conundrum here. And for no planning at all, sheer luck, this is a theorem I happen to have solved. So this was with First and Magliani, my graduate student, and myself. We were doing something completely unrelated to P groups, and we built a little theorem that actually answers this question. If you put anything on the boundary of a tensor and you apply it, the only possible symmetries have to be coordinated by something called a toric ideal. That's something from algebraic geometry. What it means is that there's a combinatorial framework. If you know toric ideals, you end up with things like fans and so forth. It's a very combinatorial structure. And in particular, it's not just any toric thing, it's what's called a binary toric. So the exponents have this property that they're disjoint and they're at most 0 or 1. So there's x powers and sorry, I should tell you what these x's are. This is a set of variables, x1, x2, x3. So in the case of here, this would be x, y, z, the different positions on the wire. So I could have something like x minus yz. And that would mean something like I have an x here and I put a y here and a z there. What this says, however, this rule here rules this one out completely. Because notice this would kick back something on this wire, something on this wire, and double on that wire. And that's not the kind of polynomial we have. It's not a binomial, and it's not got split support, and it doesn't have 0 and 1 exponents. Like this has a square. And this is not disjoint support with the support over here. So we now know from purely mathematics that if that's the correct model of the physics, you don't smooth out. The effects have to hop over particles and be spread out in a very combinatorial way, which is a really wonderful thing to know. And yet I think every physicist just assumed it was true. So it turns out no physicist ever tried to do this differential model, even though they wondered if it could have happened because it was too complicated or whatever it was. It's just that maybe they just good intuition. Net result is you don't have to worry about the other case now, but nobody really was. Okay. But the net result is, where does this come under the branch of? This is what's known as tensor isomorphism. When I apply translations to a tensor and they come out the other side as other translations, that's a tensor isomorphism. And now the question of the boundary condition becomes a purely algebra question. If I give you some configuration of tensors glued together in some lattice, and I'm moving my variables through, my operators through, which ones make it across the boundary, become the physics of the system? And that's an automorphism group question. And you can study it locally. So let's look at what you would do locally. Locally, the thing you would do is you would take a small product and you'd map onto it by a tensor product that was big. You'd make it smaller by attaching operators to shrink it as much as possible to be an approximation of the thing. And this was in work that myself and Peter Brooksbank have been working on for many years. And then the final thing is you want to boost this up to a whole network. And this is where new stuff has to happen. And this is with Martin Kasabov and Peter Brooksbank. You now look at doing the same sort of local analysis and you soup it up and you sort of have a tile, a tessellated version of tensor products. And that's the whole story. We're still at the beginning, but it's exciting because we're starting to see, oh, we can reproduce things that are predicted and we can prove things that aren't predicted. And that's kind of the right place to be when you're sort of starting something out. Anyway, that's all I wanted to share. If you want to know more, I recommend Isaac Asimov, as always. A good read, and maybe you'll learn something. Thank you for your time.
Yeah, thank you very much. Yeah, are there questions?
Well, I thank you all for coming and staying late, and I hope that you all do get to travel somewhere and see friends at some point, even if they're requiring you to quarantine for 3 weeks or whatever it is.
We just, since I looked it up, Amit had asked in the chat, I wonder who discovered the Herbert Smithite. It's definitely not Herbert Smith. Because according to Wikipedia, it was discovered in 1972 and Herbert Smith died in 1953.
Okay.
I don't know how it got its name.
And they say in homage to him.
I see.
Yeah.
Okay.
it could be another one of those things like Grosvenor bases, right?
Yeah, exactly. Right.
Yeah.
Student.
Yeah, I mean, it looks like a fascinating product. I don't know what you would do with it. I don't think you can swim in it, even though it's a liquid.
Yeah. You mean named after the first person who didn't understand what it is? That's what I've heard about Grosvenor bases.
It makes sense.
Thanks,
Yeah.
I have to go. Bye.
Thank you, Petter.
Yeah, thank
We'll
you
see each
very
other
much
again.
to all of you for
Thank you,
coming.
everybody. Everybody have a good
Yeah.
night.